All of our hydraulic structure runs are complete, so now we can do a review of hydraulic structures. So the first thing I've done is I've gone to the pre-elevation change and opened a couple of files in Notepad++. The first being cont.dat. The only thing you need to turn your culverts on in cont.dat is to set this switch right here equal to 1. But we already did that in lesson 2, so cont.dat didn't really change for this particular lesson. Now let's take a quick look at our hydraulic structures with respect to the data file. So our culverts, bridges, weirs, and random hydraulic structures that are overland or channel are assigned to this file called hystruct.dat. And if we look at the data input manual for the hystruct.dat tab, we can see these variables, and they're pretty easy to follow for line 1. Line 1 just says that S is means that that's a new structure. And the next variable is structure name. Don't use spaces in structure names. The next variable is called floodplain or channel. And the next one is curve or table. That's these two, floodplain or channel, curve or table. This one is your inflow node and your outflow node. That's these two. And then this is your tailwater switch. We call it the in-out control. This one is the head reference elevation. That's here. And then these two are the culvert length and diameter. We'll discuss those more in the generalized culvert equation, but for the short culverts in our project, when we set them up with a rating table, we don't use a culvert length and diameter because they're all less than 500 feet in length. So let's go ahead and see what we have here. For Greenway 1, switch position 1 means it's channel to channel. So let's see if we can go down here and find the eyes. And you see here that the switch positions are 0, 1, or 2, or 3. 0 is floodplain to floodplain, 1 is channel to channel, 2 is floodplain to channel, and 3 is channel to floodplain. And then there's some instructional comments below for modeling the different scenarios. The next variable was called I curve table. 0 is a curve, rating curve. Sorry, hang on a second. 1 is a rating table, and 2 is the culvert equation. So that's the switch position 0, 1, and 2. So this is a rating table. And then inlet node, outlet node is easy. And then we have the tailwater condition. So that one is called in-out control. So it's also an I, and it's right here. So 0 means it's inlet control. 1 means it's outlet control, and it can suggest revisions to the rating table. 2 means it's outlet controlled, and it can suggest revisions to the rating table. And if a revision suggestion is made, it will go to a file called reviseratingtable.out. Okay, now let's see, in-out control set to 0 means head water only. So that means the water through the system is only assessed based on the head control. If you set it to 1, there is a submergence condition as the water moves through the structure and the tailwater starts to increase, and let's say increase and possibly exceed the headwater, then the flow through the structure slows down and can stop. If the headwater exceeds if the tailwater exceeds the headwater enough that it can allow for reverse flow and water can move in the opposite direction in the structure, you then need to set the switch position equal to 2 so that you can allow water to move both ways upstream and downstream through the structure. That's the tailwater control. The next one is called the head reference elevation. So let's see where the H's are. Head reference elevation. This is an elevation above which the headwater depth is determined for the discharge rating curve or table. So if your head reference elevation is set to 0, you will use the existing channel bed or floodplain elevation in order to compute the headwater. So what it is essentially a control at which the flow through the structure can start. So let's say that we are in here on this this channel, or Greenway 1 right here, and let's say we have a ground elevation of 14 It looks like it's about 1404, 1403. And let's say we put in a head reference elevation of 1407. That means the water would have to exceed the elevation, the water coming down the channel would have to exceed the elevation of 1407 before it could move through the structure. But if you leave it to 0, that's effectively turning it off and not using it. So that means the water that comes to the structure just hits the inlet elevation and moves through the structure. Now, I think even if you have a head reference elevation and your structures are around sea level, I would be careful and test how this system works, because I've never used one that was below sea level. But that's how they work for above sea level. Let's see, that's the head reference elevation, and then these two, we leave them alone because all our culverts are short, and that's more of an advanced topic, so I'm going to leave it at that just to keep the video shorter. This is a floodplain to floodplain culvert, so let's go ahead and zoom to it. And this is what happened, is that we have assessed or ran this culvert in two different ways. The first way that we ran it was to run it with no elevation corrections applied to the front or back of the culvert. Let's see, here's our elevation polygons right here. So the first time we ran it, we didn't apply the elevation correction, and the second time we ran it, we did apply the elevation correction. Probably didn't make much difference on this one because it's a very large amount of water moving down to this system and collecting on this culvert. So let's go ahead and skip this one and move down to a different one that rating table might have had more of an impact on. Let's try culvert 125, or better yet, maybe culvert 126. So culvert 126, we have given an elevation correction to the upstream side to try to allow water to get to this structure. So let's take a look at the results from these two structures. We'll just ignore that message. It just means the Google server was not available for a few seconds there. Let's see here. Let's go to, let's do this. What we'll do is we're going to set our run settings to pre-elevation change, and then we'll use this guy to plot the discharge through that structure with that before the elevation change came into effect, okay? And let's just take a quick, oh, I can't take a screenshot of it. We're going to have to take a screenshot of it in our mind. And now let's do that again, but this time, okay, so let's see, we're just above 6. Now let's try that again by setting the run settings to the post elevation change. And then let's get that structure, the new structure, and see if that increased our flow through the structure. And yes, it did. No, is that right? The right structure? Wow, it really did. So much so that let's see what our rating table allows in this structure. Oh, that's not our rating table. Let's pick up our rating table for that structure. So that is allowing up to, okay, so it says at 2 feet of depth, it can take about 40 CFS through the structure. So we weren't getting 2 feet of depth on this structure before because we didn't have our elevation correction applied. And then when we made so we were only getting about 6 cubic feet per second drainage through this structure. And then when we made our elevation correction, we are now allowing, it says that this particular structure can allow, at 2 feet of depth, can allow about 40 CFS through the structure. And this is interesting because not only are we getting the report of the 40 feet of depth allowed through the structure, but we're also getting that it's available upstream. So if it wasn't available, we wouldn't get this much. So not only are we getting it down in this area, getting enough flow down through this street into this spot, we're also getting it to our structure. So that's interesting that changed so significantly just because of an elevation change. Let's go look at culvert 122. because that is one that we did an elevation correction and applied a levee to, and something else weird is happening to this one. So let's take a look at, so now I want to load, well, let's do this. Let's load, oops, sorry. Yeah, that's okay. This is the structure. This is structure 6, and it looks like it can pass 50 CFS through the structure. But because of this weir and this limitation right here, we might not get 50 CFS. And also on this side of the structure, because we've effectively cut our basin like by 3/4 of its area, we may also find that we are not able to fill this structure correctly. So let's look at the maximum depth. I loaded the maximum depth. Oops, let's get the Google satellite down here. And where did that go? Oh, it's under our elevation. Sorry about that. I need to put my elevation below my results. Let's see. So let's hang on. Let's put our elevation right here. Okay, there we go. So now you can see that in one of these runs, I can't remember which run I grabbed, but in one of these runs, this would be the final depth, or the maximum depth, which is also in this case the final depth because this is a closed basin. And as we force more water through this structure, you'll see this kind of become exacerbated because we not only did we cut our basin by 3/4, but we also lost our drain system over here. So we'll need to be aware of that and either put a boundary control in here or something to kind of allow this to drain. So this result is not realistic or a good result right in here. We would need to extend our project over here. But the purpose of the project is to show you how to set up data, not to get everything perfect. Okay, so let's see the difference between of this structure with, and so this is 50 before the elevation correction, this is getting 50. Post elevation correction, this is getting 50. Now let's change this back to the pre-elevation correction. So here, let's go back to pre-elevation correction, and we will hit that again and see we're getting a little bit less. So it's not a ton different in this particular case. And that's pre and post elevation correction. Now let's see what happens when we changed it to the generalized culvert equation. So let's change it one more time. So this one needs to go to run settings, needs to go to generalized culvert equation with the elevation correction. And let's see what this guy says this time. Interested to see. Wow, it's like very close to the rating table, which makes sense because that rating table was, it was developed from a generalized culvert equation. So that makes sense that they're very close. So I'm glad to see that. That's great. But I would say maybe we should, well, until we can sort things out down here on this side, there's not much we can do to make this structure work. It doesn't make any sense to turn this to like a tailwater control or anything because this flow is being confined in here. All right, now let's look at maybe one more. Let's see. I guess we have one more generalized culvert equation. I don't quite remember what we had in this structure. Yeah, I think it was pretty close to 100 CFS, so it looks about the same. Let's double check that this is set to the correct location. Flow 2D settings. Yeah, generalized culvert with correction. Now let me check one more thing because I did want to show you the difference in the culvert equation data file. So let's grab the hystruct.dat file and let's get down to culvert 9. So you can see the difference in the data file. So you can see here culvert 9 has a different data set because this is setting up the generalized culvert data. So if I go back here to the dial or DAT, the hystruct.dat manual, and we go down here to the F line, this F line matches this line right here, line 75. And so it's structure character equals F, and the type C, type entrance, type EN, culvert, and KE, cube base, and malt barrels. So those are the variables that we set up in this location. So if I pick up culvert 9, you'll see that these are the variables we set up here in here. And we already went over these variables. Entrance type or type of the culvert, 2 means that it is a circular. And then 1 means that its head wall is, I guess, like blunt, it's not projecting. This is your N value, this is your loss coefficient, which is also for a blunt edged opening. This was a culvert width, but since it's a circular culvert, we'll be using this instead. And this 3 means multiple barrels. And 250 is its length. And we did see that we were getting 100 CFS through both structures, so that was good to see. I mean, one structure was created, one of the rating tables was created from HY8, so it should be very close to the secondary structure. And then of course here's the 112, the only difference being that this one is a box culvert, so it's got a height here and the width here, and 1 means box instead of 2 means circular, and then this is like wing wall 30 to 75, N value, K rate for the blunt edge, it was like maybe partially smoothed or something, and then that was the width, and then there was only 1 barrel in this case. So 3 barrels in this one and 1 barrel in this one. And that's basically it for the hydraulic structure overview. So we'll shut this one down, and this will be the last lesson for this series, and then we'll go in and add a mapping and project review that's going to be somewhat generalized for the more advanced topics, or maybe be skipped in that one.